Okay, we want to do three things. We want to draw the electron configuration, we want to draw the orbital notation, both for bromine, and then lastly, we're going to show all possible sets of quantum numbers that could represent the last electron added to bromine. Okay, so bromine is right here. It's on the fourth period, and here we have the S block, here's the D block, the D filling elements, and the P filling elements. So our last electron is going to be 4p5. So we want to do everything up to that. All right, so we have 1s2, 2s2. Okay, so 1s2, 2s2. Then we're going to go over here to 2p6, 2p6, and then 3s2. And then we're going to jump over here to 3p6. And then we go down to 4. So that's going to be 4s2, which comes right before 3d10. And then lastly, we've got 4p, 1, 2, 3, 4, 5. 4p5. Okay, so that is the electron configuration for bromine. Now we're going to do orbital notation. This is the notation that includes the boxes. So we're going to draw the boxes to represent each of the sublevels, and then we'll divide them up into orbitals. So this is 1s. Of course, that's both an orbital and a sublevel. Then 2s, and then 2p. So this 2p represents a sublevel, and now we're going to, those three boxes are the orbitals on the sublevel. Okay, then we have 3s. Again, here's our p sublevel, our 3p sublevel, and it's got three boxes or three orbitals. Next is going to be 4s, and then we have 3d, which has 5 orbitals, 5 boxes, 1, 2, 3, 4, 5, that's 3d. And then lastly, we've got 4p with 3 orbitals represented by 3 boxes. Okay, now watch how I'm going to put these in the right order. I'm going to put them in order of how they would fill up. We're going to show an up arrow and then a down arrow for 1s. So we fill that before we go on to 2s. And then 2p, we half fill, okay, because they are all the same energy, they're degenerate, they're all the same energy. This electron doesn't want another one coming in here if it can help it. So he pushes this one over, the second one, and then the second one pushes the third over. Well, now it's too much energy to shove him over to 3s, so we have to fill these orbitals. And now we're going to do 3s. We fill him. Okay, 3p, half filled. Notice these all have parallel spin. We would not do something like this. This would be wrong. So we wouldn't do that. Okay, so that's wrong. And we wouldn't do this. Okay, so that's wrong because we want parallel spin and we want to half fill the orbitals first. Okay, so then we're going to go back and completely fill them. 4s gets completely filled because there's not enough energy to kick from 4s over to 3d. And then we fill in the 3d, half filled with parallel spin. So this is parallel spin all going up. And then we fill them with the down arrow. Okay, and then in the case of 4p, we're only going to have 5 electrons. 1, 2, 3. I'm sorry, 3 electrons. That's going to be 5 on the 4th level. So this is going to have 3 electrons. No, I was right. 5 electrons. Sorry, confusing myself here. So this is going to be 4p5. So it's got 7 electrons on the 4th level. Okay, so again, 4p has 5 electrons. because bromine is going to be 1, 2, 3, 4, 5 on the fourth level in the p block. Now we want to put all the possible quantum numbers for the last electron that goes there. Well, because these are all equal, technically the last electron could be any of the 6. Okay, it could have been this one, this one, this one, this one, this one, or this one. If we were to remove an electron, which usually doesn't happen with bromine, but it's possible, could remove any of those because they are all of equal energy. So we would need to show 6 sets of quantum numbers. Okay, so 6 sets. 1, 2, 3, 4, 5, 6. Because we've got 6 parking spaces that are equal, the last electron could go into any spot on here could have been the last electron. Even though we half filled them with parallel spin and then we went down and this spot's open. Technically, because they're equal, all of them or any of them could have been the last electron. So the first quantum number is n. N equals 4 for all of them. N equals 4. Okay, and we're going to separate these by commas. We're just going to write it as a set like you would in math. Then the second quantum number, so this is 4, represents that 4, n equals 4. And then the second quantum number is L. L is represents the sublevel, in this case P, and you should remember that P corresponds to 1. S corresponds to 0, P corresponds to 1, D corresponds to 2, F corresponds to 3. These are all P electrons, so we're going to put a 1 for all of them. Okay, now the quantum numbers that are different can be the last 2. So let's kind of review quantum numbers here. Let's take a look. Here's my p orbital. So let's call this 4p. Now, in quantum numbers, we number these with a 0, a +1, or a -1. These are all equal because they're on the 4p sublevel. So that third quantum number could be any of these. But there's only 2 electrons that could go on this particular orbital. So we will only have 2 with a -1. So I'm going to just give us 2 with -1. Doesn't matter what I start with. I could have started with 0. And the next one's going to be 0. And then the next one will be +1. Okay? So I have 2 electrons on the -1 orbital, 2 electrons on the 0 orbital, and 2 electrons on the plus. Now, how are they different? Well, we have an up arrow and a down arrow, represented by +½ and -½ So I cannot have 2 sets of quantum numbers that are the same, so this is going to have to be -½ because everything's the same except that last number. So then this will be +½ and -½ since they both go on the 0 orbital. And again, +½ -½ So those are the 6 sets of quantum numbers that are represented by the 4p. Since all those electrons are equal energy, any of those sets of numbers could represent the last electron to go in.